greater than equal to 0 and less than equal to pi, then this quadratic equation has real roots. So we need to check whether this statement is true or false. So this is the given quadratic equation with this given interval. To check whether this quadratic equation is having real roots or not. And when the quadratic equation is having the real roots, if the discriminant is greater than equal to 0. So let's check whether the discriminant is greater than equal to 0 or not. See, for D positive, we are having real and distinct roots. For D equal to 0, we are having real and equal roots. For D less than 0, we are having complex roots. Now from these two, we are getting the real roots, right? Just to check for the real roots, we write the discriminant to be greater than equal to 0. Fine? Alright. So let's check whether this quadratic equation is having the discriminant to be greater than equal to 0 or not. So the discriminant is b square minus 4ac. That is cos square p minus 4. What is a? It is cos p minus 1 into c. That is sine of p. Right? So that is equal to cos square p minus, let's open the bracket, it is 4 cos of p sine of p plus 4 sine of p. We need to make the perfect square, and for that let's add and subtract 4 sine square p. So from these three terms we are getting cos of p minus 2 sine of p whole square, and rest of the terms, let's take 4 sine p also common. So let's write plus sign here, 4 sine of p. This is 1 minus sine of p. Is it okay? Fine? Alright. Now first term is positive, right? Because of the square. Let's check for sine of p. What is the interval given to us? P is belonging to closed interval 0 to pi. Let's check in the quadrants. This is 0, this is pi by 2, this is pi. Now sine of p is positive for these two quadrants, right? Sine of p is not only positive but also equal to 0. Either it is equal to 0 or it is greater than 0. Because sine of pi by 2 is 1. Sine of 0 is 0. Sine of pi is also 0. So the values of sine p in the interval from 0 to pi is greater than equal to 0. So this is greater than equal to 0. And what about this value? 1 minus sine of p for this interval. See, what is the range of sine p? It is from minus 1 to 1 for all p belonging to the real numbers. For every p belonging to the real numbers, the range is minus 1 to 1. The value of sine ranges from minus 1 to 1. Now sine of 0 is 0. So subtracting sine of 0 from 1, I will get the positive value. At pi by 2, I am getting the value of sine pi by 2 as 1. That means if I subtract 1 from 1, I get answer to be 0. From 0, the value of sine increases up to 1. And from pi by 2 to pi, the sign of value decreases to 0. That means if I subtract any value of sine p from 1, either I get the value 0 or I get the value positive, right? So 1 minus sine of p is also greater than equal to 0, right? That means this complete discriminant is greater than equal to 0. Yes? And if the discriminant is greater than equal to 0, then the roots of the quadratic equation are real roots. So this discriminant is greater than equal to 0. Reason, sine of p is greater than equal to 0 and 1 minus sine of p is also greater than equal to 0 for all p belonging to the real numbers. Hence, this equation has real roots, right? So this statement is true.